Okay, I decided to experiment with this little, voltage divider bias for JFETs, just out of curiosity, and I haven't fully investigated it yet, so some of this stuff is going to be news to me too. Um, when we look at it, um, okay, but yeah, this is the circuit, pretty much verbatim what I built. Okay, the only difference is I ran it at 30 volts here just so on the simulator you can see what happens with the voltage divider here. See, it's a 2 to 1 ratio here, so that's a voltage division of from 30 volts down to 10 volts. But how you actually figure, what kind of current's going to flow through your device is you actually take this 10 volts here and you divide it by your resistor value here. In other words, you assume when you're doing the calculations, and again, this is a rule of thumb. It's, a quick and dirty way of doing it. And it'll be approximately correct, so you divide 10 volts, by 3.3K, and that gives us about 3.03 milliamps. In practice, it's closer to 3.5, but again, it gets you in the ballpark, and you can see what the voltage is, under bias conditions. And this is what the operating point, slated to be at this voltage. But that's not the voltage I'm running my test circuit at, because I'm using 25 volt JFETs, not 30 volt JFETs, so I don't want to blow anything up. So basically, here let's probe these parameters. You can see it's supposed to be an output Q point of about 15 volts, output, and um, then about 8.3 volts on the input and about 10 volts, on the across the source resistor. So, and this gets annoying. Um, okay, so anyway, here, damn this thing. Well, let's see. Yeah, you can see the instruments. Okay, so here, is our little JFET. I used an MPF 102. I did put this little capacitor here just to see if that improved the frequency response, which we'll get to um, in a little bit here. But it didn't help. So anyway, these are all 1 microfarad caps, just like in the sim. So, all right, but let's take a look at what we got here. Let's see, the gate voltage. Um, Here's our input. Okay, wait for the meter. 8.149 volts versus the 8.3 volts false stat predicted. Looks good, not unreasonable. Let's look at the let's see, yeah, the out. Well, I'm probably got a short circuit something here. Yeah, let's look at this pin. Okay, that's our output pin at 15.8 volts. False stat predicted 14.9. So that's not too bad. And then let's look at the source resistance here. If I don't short something out in the process. Yep, 9.1 volts if false stat predicted 10.1. So again, not unreasonable. So again, the FET and false stat, I tried to mimic it as close as possible, to just an average FET. This MPF 102 is probably more like 5 milliamps or something like that, so it's nowhere near what this circuit is trying to simulate. So, at the end of the day, well, that's pretty good, for the biasing point scheme. So, it does require fairly high voltages, I think, to bias JFETs this way. But, Let me run the simulation here a little bit, and you can see the predicted gain on it's about 8.5. So as you can see right here, it's about 8.5. So let's go over and let me go ahead and run our analog discovery. And so I'm inputting a signal of 100 millivolts, just like on the scope. Now I got mine set to like 174 kilohertz. But you can see our gain prediction is about 8.5, you know, with a sine wave on it. So, you know, our peak-to-peak span output is about 1.8 volts, and Falstat is predicting about 940 millivolts for a 100 millivolt input signal. But yeah, so I mean, there's certainly a discrepancy there, but still the gain prediction is, you know, about accurate. So, because Volstat's actually, you know, predicting 1.6 volts. I take that back. So it's actually pretty similar. So, you know, for 200 millivolt peak-to-peak input, I just wish this fucking Volstat had a peak-to-peak output reading. That just really pisses me off. It's annoying as shit. But the fact of the matter is, yeah, because you can't display peak-to-peak, you know, on anything on that fucking thing. It doesn't have that option. But so anyway, it looks pretty good, you know, at you know, at the frequency we're at. But let's look at how much voltage swing we can get out of it. Oops. Shit. Stupid offset. Okay, so our voltage swing, you know, is about, you know, 10 volts peak to peak where I've got it. But it's going to start fussing at me over here. God damn it! Stupid offset. It's a fucking idiotic thing to put in there. Anyway, yeah, about 10 volts. So let's up the ante. And yeah, it's starting to deform the waveforms, that's for sure. So, but we're getting a maximum peak-to-peak swing of about 16 volts out of it. So that's not, you know, it's you know, it's got good spread, you know, so there's a lot to work with, but would hope so, you know, with a 25 volt input on this thing. But you know, getting it down to more manageable levels, get it down to, you know, half a volt or something like that. Yeah, it's pretty sine wave like at that voltage. So let me lower the fuck, I hate that offset thing. Let's see. Yeah, we got 500 millivolts on our signal, so let's convert it and see what a square wave looks like. Wow, looks like sharks are swimming around almost. Yeah, that's why I was trying to put that extra capacitor there to see if it improves that, you know, because yeah, I mean, this just like that last circuit I tested, you know, with the current source, you know, there's some, you know, it looks like, you know, capacitive issues here. It's just bizarre. I mean, because this is supposed to be a pretty high frequency JFET. It's just shocking that it, you know, has that issue. You know, I'm not sure what is that's causing it yet. You know, lowering our signal back down to even 65 millivolts, you still see it. I mean, it's still prominent, but that's because the rise time of the square wave is the same. Again, it's rise time related. But still, I mean, you know, I wouldn't think analog discovery's rise time is that high. I guess I don't know how fast it is, but still, you know, it's just curious, you know, because I haven't seen that, you know, as a regular feature, you know, especially at only 146 kilohertz like we're at right now. So it's just bizarre, you know. But you know, we up the frequency. You know, the wave shape stays the same. It's definitely rise time related. So I don't know. I'm not sure what to make of that just yet. But it does affect its square wave performance. Obviously, it's you know, taking some harmonics off of it somewhere. Still not sure where. Might be an inductance issue, I guess. But anyway, triangle wave looks a bit distorted. you know, for a trapezium, you know, which is supposed to look like that, you know, not that great. Let me, well, geez, let me lower the signal down to 100 millivolts like we got in our sim over there, and let's go down to 200 on that. So yeah, we still got a gain of about 9, you know, but again, you know, 157 kilohertz is pretty distorted. You know, when you get down to, you know, like 80 kilohertz, let's see what it looks like. Okay, still, you know, kind of rounded on it, not perfect. You go to a square wave, you know, you still see the rounding. I mean, it's a usable waveform for like digital or something, but still, it's not very faithful. But like I said, you know, you'll notice, you know, again, it's strictly rise time related, you know, that it just rounds off these corners. I just don't think I've seen that, you know, with all the amplifiers I've tested. That's what's puzzling about this. Seems to only be these FETs that actually kind of consistently do that, you know. But anyway, you see big improvement. You know, it's kind of more like a slew rate issue almost, but not quite, but almost. It's almost like that. It's reminiscent of that. I'll put it to you that way. You know, because when I go to a waveform like this, you know, at 20, you know, again we're down to 20 kilohertz again. That's kind of what the last circuit I experimented with, that, you know, that current source-driven FET circuit sort of did. So, but this doesn't have that. I mean, it's just like a minimal circuit here, and but yet it still kind of behaves the same sort of way. I mean, I don't know. It's just shocking. I mean, surely, I mean, they, you know, must be a FET capacitance thing. I just didn't think these JFETs were supposed to. I mean, I thought that's what was so badass about them. They're supposed to be low capacitance, you know, so you could use them to high frequencies. And again, indeed, this MPF 102, you know, has specs going out to the gigahertz range. So, I mean, I just wouldn't expect it. If that's true, I wouldn't expect to see square waves doing this at such relatively low frequencies. So, you know, because you start to even see rounding on this, you know, at about 48 kilohertz, and, you know, square wave, it's definitely there. Again, it's a rise time thing. So, I don't know, it's just sort of puzzling that it does that. So, let me vary the amplitude, you know, to contrast that with the board we did the other day. Remember the board, if you saw the video, you know, the board I was doing with the constant current source, if I did this, you know, there was a definite lag between this yellow wave, which is our output, versus the blue wave, which is our input, and that was probably the response of the constant current source. It was definitely doing something there, even though that's really supposedly strictly for DC bias. So, I mean, obviously it interacts with it somehow. So, again, like I said before, you know, I don't have a lot really of experience with JFETs in particular, so it's, you know, this is all a learning curve. So, but yeah, I mean, again, I wouldn't be surprised, you know, if this were, you know, this kind of thing occurred on one of the circuit boards I routed, you know, because like I said, I typically will do this. I remove minimal copper and all. That's got to really increase the capacitance, you know, between all the traces and stuff, because you got all these copper landings, you know, throughout there that really aren't grounded or anything. They're just floating. That's one of the ways I test for short circuits when I do these stupid boards. That's why I hate them. I mean, it takes forever to remove the burrs, and, you know, but boy, it takes forever to route out all that copper too, and wear out all your tools and wear out your machine. So, you know, that's why when I make circuit boards this way, my expectations aren't super high, but, you know, but they're interesting to test. I wouldn't be surprised if this had done that with that, but I'm actually rather surprised because these breadboards have actually been better frequency performing from the tests I've run so far than, you know, most of my circuit board versions of circuits. But at any rate, let's go ahead and run a network analysis on this, because I haven't done that yet. So I'm going to set that from 100 hertz up to 2 megahertz, and signal level, we'll go ahead and set it to 100 millivolts since that's what we're testing, and let's run a sweep and see what the gain looks like. Okay, that's our low end. I didn't give a lot of I put a lot of effort into the capacitor. I'm surprised actually though, but I guess that's because it's voltage divider bias, so that's making the cutoff frequency higher than it was on the previous amp. So, but that's no big deal. I'm mostly interested in the high frequency performance anyway. So, yep, this goes out to about 100 kilohertz, and then it starts really rolling off. It's probably down 3 decibels by 200 kilohertz. So, not a huge bandwidth. I mean, you'd expect it to go at least 1 megahertz, right? This is going to be with a sine wave. Um, so, let's see. Hold on a second. But yeah, if you'll hold on for a minute, I wanted to try an experiment. Let's see how component JFET agnostic this circuit is. I'm going to grab like a J111 and stick it in there just for shits and giggles. See what happens, What the fuck? Well, with a J111 in there, not surprisingly, it's nothing. I would have been shocked if it would have done anything given the current readings on that JFET, so being as extremely high as they are. So this circuit ain't that agnostic. So, but let me try a different JFET here. It's a 2N5951, so I'll try that real quick. Let me turn it off and let's see what happens. I don't really know if the pinout's the same on this. I guess I ought to test that first. Hold on. Get this thing in here and see what the results are. Okay, so an NJFET, the gate being pin 3, that's different. That's backwards from what it usually is. Usually pin 1 is the gate on these. I'm glad I tested it. Yeah, so it's saying pin 3 is the gate, so I'll have to put that somewhere else. Put it backwards, and hopefully this thing won't matter. The drain and source, like most of these. Okay. Hopefully this doesn't explode. I only have 10 of these. Let me turn the voltage down a little bit just in case. I don't even know what the voltage rating is on that. Okay, now it's not doing nothing, so yeah, it's definitely not doing anything. So I probably put it in backwards, or it doesn't work backwards. There's no current coming out of it at all. Let me toy around with this a second. Okay, I just had the damn thing in the wrong holes. Like I said, breadboards, don't like breadboardings that much. But yeah, okay, so here's our output waveforms. This 5951, which I got the data sheets out. That was actually hard to find for some reason. It's a 30 volt FET, so I could go higher voltage with it a little bit, but let's see. So we got a gain of about 8.7 or so. So very similar performance, I suppose. Let's see what a square wave looks like. Yeah, still pretty rounded, although maybe not the same level. Let's see. Looks similar performance though, but the curve looks like it might be a little different, but I'm not totally sure of that. So let's see what its frequency response curve is. Let's see, run a single leveling off, about the same gain, and you know, roughly the same roll off too. So yeah, I don't know, um, that one's supposed to be an RF amplifier, so let's see what its frequency parameters are, see how much data they give us here. You can see this over there instead. Let's see. Okay. Pretty typical performances, somewhat similar to the MPF 102 a little bit. Maximum IDSS might be a little higher, might not be, I don't know. Already is on to 150, 6 and 2 picofarad. I mean, that's not too unusual. I mean, I think it's a similar character. So, but again, these aren't that much greater than, many common bipolar transistors. So, I mean, but again, I still haven't seen this kind of behavior out of many of my bipolar transistor amps. I mean, you do get it at some point, but I mean, I don't know, those frequencies that you get it at seem really extremely low, though. Only 80, 60 or 80 kilohertz, it's deformed like you've seen. See what its FT is, if it's got anything like that on here. What it's meant for frequency wise. Sometimes they're kind of coy about that. You got to look at the graphs. Transconductance, micro, whatever, what output conductance. Okay. Everybody likes to do it different. Oh shit, they don't even have any graphs. Well, anyway, yeah, you can't learn too much about this. It's supposedly obsolete anyway, so like you see here, obsolete. Okay. Anyway, yeah, so interesting, and just something to consider in your biasing options of JFET. So you'll have to run your own tests, but I'll tell you, most of the other amplifiers I've tested with JFETs, if I recall correctly, didn't have this bad a square wave performance at these lower frequencies. I mean, that's just really kind of shocking that both of these two JFET agnostic bias circuits I've tested out of this book, are, I don't know, just they don't perform well with square waves like I kind of expect. Like I said, I'm not quite sure what the cause would be. Again, it's not amplitude dependent at all. I mean, it's definitely transitional in nature, which you'd kind of expect there to be a response related to that if the rise time pulse is fast enough. But it's just really weird to kind of see this capacitive phenomenon, and it's persistent, with any square wave, and again, you even see dodgy performance on the trapezium, it's still relatively low frequencies, so that's starting to really round where we have it right now. I lower it and it's an improvement, but it's still rounded off, probably by the same degree. Again, we're talking 60 kilohertz. I've just, given the low levels of signal, I'm putting 100 millivolts, and then with the gain only being like 6 to 10 or so, 8 like we show here, it's a little underwhelming. So I'm a little confused about JFETs as being great, badass high frequency amplifiers and shit. I don't get it. Again, like I said before, that's the one thing, and my opinion on that has not changed, that these FETs they don't have a lot of gain to work with, and as a result, you can't really linearize them very well, like with feedback, like you can a bipolar transistor. That's why you can make bipolar transistors behave at with pretty low distortion, even though they're a discrete device. Um, but man, because I know FETs are highly prone to distortion, and okay, maybe it's the square law thing. I've heard them talk about something like only the second or fifth harmonic or something like that shows up because of it being square law, and then like nothing else. I have no idea. Um, you know what the argument was. It's for real. I just heard it mentioned in like on ESP Guy's website. An ESP Guy, by the way, if you look at his JFET website, he has some much more elaborate biasing schemes for JFETs, on his JFET articles. But like he says, it's kind of a lot to go through for a discrete component when you just use a JFET input op amp most of the time, and so it's just I don't know. It's just bizarre that yeah, there are these relatively JFET agnostic circuits, and again, he's got some more on his site that are much more elaborate, involving really good constant current sources and so forth, good and stiff ones. They actually have higher gain too, but but the degree of trouble you got to go through to do it is pretty extraordinary, like he kind of points out. So that's why he says he generally doesn't include JFETs in the circuits, because it tends to be too big of a headache for his, the people that actually build some of his circuits. So, which is kind of what he does. He sort of sells circuit boards for a lot of his audio amplifiers and stuff on their kits. Well, not really kits, but it's a circuit board, and you can buy your own components, evidently. But at any rate, he has some good articles on his site, though. And again, I'm not affiliated with him at all. Never even talked to him. But yeah, okay, that's something else to put into your cap, though, as far as another biasing scheme. But again, JFETs are still always going to be pretty nonlinear. That's what makes them rather good mixers, actually, nonlinear mixers, because they are rather, undeniably nonlinear, even more so, I think, than you can consider diodes, depending on where you're operating them anyway. But these are like across the board nonlinear. It's if you have any significant signal swing at all, you're going to see distortion because of that. So maybe that's some of what's going on, but I don't know, because JFETs, all the JFET amplifiers I tested, especially like the source biasing ones I did earlier, much earlier, several week or two ago. I just don't recall them exhibiting this kind of behavior at low frequencies. And again, they're low gain too, like 6. So again, you could put larger signals in them and so forth, and it's just this guy, of course, covers that same scheme too, but can't really thumb to it with all this crap lying around on it. But at any rate, it's just something else to put in your ball cap. So if you ever need to use JFETs, well, these make them a little more practical, but I still say having a component curve tracer would still be a really good idea, because you can actually look at the family of curves, and if you want to draw load lines on it and shit like that, and especially try to do fancy things like bias it in the ohmic region and stuff, looking at the actual family of curves, not just the transconductance curve, would be useful. So anyway, cheers. That's it for this video.